class. Class is being recorded now. Anyone's ready can go ahead. Let me see whom I'm missing. Zakia.
Hi.
Hello.
Can you miss me?
Yes.
This is a 5.5 on chapter 5, question 5. A filling station is supplied with gasoline once a week. If its weekly volume is of cells in thousands of gallons, is a random variable with probability density function. Then x is between 0 and 1. F of x equal to 5 parentheses 1 minus x to the power 4. What must be the capacity of the tank be so that the probability of the supply being exhausted in a given week is 0.01. So first of all, consider when x approaches to 0, that means no gasoline. So the probability being exhausted would be 100%. So then instead of 0, we give a variable c, the amount of the volume x between c and 1. So the probability become 0.01. So you just plug into the value and calculate it. So we got this, and then we can use substitution, and after we integrate, we got this, and we set it equal to 0.01, and we find the c is equal to 0.6 in 1,000. That means 600 gallons.
Great. Good job. Great. I like this. Okay, thank you. That's Jie. We're using our previous knowledge now.
I want to present 5.10.
Okay. Oh, it's gone.
Yeah. Okay. 5.10. Trains headed for destination A arrives at the train station at 15-minute intervals, starting at 7 a.m., whereas trains headed for destination B arrives at 15-minute intervals, starting at 7:05 a.m. A. If a certain passenger arrives at the station at a time uniformly distributed between 7 and 8 a.m. and does get on the first train that arrives, what proportion of the time does he or she go to destination A? So that I drew the timeline. So the proportion that he or she goes to destination A between 7 and 8 a.m. is the integral from 5 to 15 of 1/6 d of x plus the integral of 20 to 30 1/60th d of x plus the integral of 35 to 45 1/60 d of x plus the integral of 50 to 60 1/60 d of x, and that is 2/3. And then B, what if the passenger arrives at a time uniformly distributed between 7:10 a.m. and 8:10 a.m.? So the proportion that the passenger arrives uniformly between 7:10 and 8:10 a.m. is the integral between 10 to 15 1/60 d of x plus the integral of 20 to 30 1/60 d of x plus the integral of 35 to 45 1/60 d of x plus the integral of 50 to 60 1/60 d of x plus the integral of 5 to 10 1/60 d of x, which is 2/3 as well.
Okay, I want to ask you a question.
Yes.
So why the integral set from 5 for the first one for A from 5 to 15 of because 15 minutes interval.
Yes.
So starts at 7:05. Why starts at 7:05?
That was the time for the part B. That's not for that
That's
one.
the part B.
Yeah.
Okay. All right. So 5 to 15. So 10 minutes. I see. Okay. So for B.
So for question A, it starts at 7 a.m. to 8 a.m. So the first interval for A is 7:15, and then for B starts at 7:05. So and then it goes to 7:20.
Okay. So my question is the lower limit and upper limits. You see, for A, the lower limits is 5, 15, 20, 30, 35, 45. Can you explain that? 50 to 60. The lower limits and the upper limits.
So for A, it's the station. It's between the time of 7 to 8 a.m. So if 5 to 15. Yeah, because destination B arrives at 15 interval starting at 7:05.
I think I got it. It's a 7:05, right? You start
Yeah, it
counting
starts
from
at 7:05 for destination B, but it starts at
right.
7 for destination A. Like it's on the question.
Oh, okay, between 7 and 8 a.m. No, it's on the right. It's on the before A actually. It says, hold on. A arrive at the
Yeah,
train
it's on the
station
question.
starting at 7. Okay, starting at 7. Okay, my question is still your lower limits and upper limits. Just explain the first one. Why is 5 to 15? I'm not getting it.
Because the lower limit is 5 for destination B. And B starts
for destination B, not for
from,
question B. Okay, I'm confused with this AB.
uh-huh.
Okay, got it. All right. Okay, I have no more questions. Thank you. Very nice.
Thank you.
Mm. So let's show you.
Hi, Professor. I'm going now.
That's Yongxin. Sorry.
Oh, that's Yongxin. I'm sorry.
Yeah.
Okay. So I had a J and Yongxin. Okay, Kara, go ahead. We need to see your screen.
Okay, Professor. I'm going to share it.
Okay.
Can you see my screen, Professor?
Yes, I see you
Okay,
now.
I'm going to present question 5.3 of chapter 5. For the positive c, could the function of x is equal to c into 6x square minus 5x in it x greater than 0, less than 2 over 3, otherwise 0, be a probability density function? If yes, determine the value of c. Repeat for function of x is equal to c into 6x square minus 5x, where x greater than 1 and less than 4 over 3, otherwise 0. So for this question, for a function f of x to be a probability density function, it's necessary that the integral, which has the limit of minus infinity to infinity, function of x dx is equal to 1. It should be must 1. C integral, which has the limit given in the question, that upper limit is 2 over 3 and lower limit is 0, which is in the first part of the question, into 6x square minus 5x dx is equal to 1. After applying the integral, we will get 2x cube minus 5x square over 2, which has the limit of 0 to 2 over 3 is equal to 1. After putting the limit of the integral, we will we solve it, and we will get the answer, the value of c, which is equal to c is equal to minus 27 over 14, which is a negative number. We can say that for the positive c, function of x cannot be a probability density function, because in the question it asks that function is a probability density function or not. So for positive number, it's not the probability density function, but for the negative number, it's a probability density function. And now we are going for the second part. Now we have to solve the second part, which is function of x is equal to c into 6x square minus 5x, which has the limit of x greater than 1 and less than 4 over 3, otherwise 0. C integral 1 to 4 over 3 into 6x square minus 5x dx is equal to 1. Similarly, for the previous one, we have to apply the integral, and we will get 2x cube minus 5x square over 2, and the limit 1 4 over 3. And after putting the limit, we will get the value of c 43 over 54 is equal to 1, and then we will get the value of c 54 over 43, which is a positive number. So for this part, we can say that this function is a probability density function for value of the c 54 over 43. Since this is a positive number, that's why it's a probability density function.
Nice.
Thank you,
Okay,
Professor.
nice. Thank you. Okay, next one.
Hello, Professor.
Hey, Catherine.
Can you hear me well?
Yes.
Okay. So I'm presenting 5.1. Let x be a random variable with probability density function of c times x minus 3 over x squared. 2 is less than x and less than 4, or 0 otherwise. Part A was the value of c, and part B was the cumulative distribution function of x. So for part A, we use this formula, the integral of upper limit infinity and lower limit is negative infinity function and dx. So when we compute the integral, we get that c times integral of upper limit is 4 and the lower limit is 2, x minus 3 over x squared dx equals to 1. And when we compute this integral, we get that c is equal to 4 over 21. So we're going to use this c for part B for the cumulative distribution function of x. Since we define the x, for this new integral, the upper limit will be x and the lower limit will be 2. And we put c in here, 4 over 21 times x minus 3 over x squared dx. And after we compute the integral here, we get that the cumulative distribution function of x is 4 over 21 times x cubed plus 3 over 2x equals 7 over 2.
Equals 7 over 2 or minus 7 over 2? Minus.
Minus 7 over 2.
Minus 7 over 2. Okay, you did very well. I remember last class you were a little bit frightened.
Yeah, yeah. I went back
Probability
and
numbers.
review, so I understand it.
Yeah, yeah. Very nice. Good. Good job. Okay. All right, next one. But you see now how mathematics, it's a cumulative, right? Using the integration skills for probability. Okay, Zakia, go ahead.
Okay, so I'm presenting 5.4. The probability density function of x, the lifetime of a certain type of electronic device measured in hours, is given by fx 10 over x squared, where x is greater than 10, 0 where x is smaller than equals to 10. So we have to find probability of x is greater than 20, and what is the cumulative distribution function of x, And part C is what is the probability that of 6 such types of devices, at least 3 will function for at least 15 hours? What assumptions are you making? So for part A, we have probability to find probability of x is greater than 20, which is the integral of the upper limit is gonna be infinity and the lower limit is 20 fx dx. You have fx given 10 over x squared. We're just gonna solve the integral, and we're gonna put x value as infinity and 20. So we know that when it's infinity, it's gonna be turned to 0, and then when it's 20, it's 10 over 20. And the final answer is 0.5.
Hold on one second. Hold on one second.
Yeah, sure.
Okay. Remember, this is the integration involves infinity sign, right?
Yeah.
If I have to be critical, you have to use the idea of limit, because we can go right ahead to integrate infinity at infinity. Infinity is just an idea, but it's right. You are right. The answer is right. But however, to be mathematically correct, you have to use a limit. You use a dummy variable, maybe t, maybe n. You run into n, then you let n run into infinity. All right. Okay, but I guess it's
yeah. I have that on my mind, but I just write it like that. So
yeah, mathematically we cannot integrate it.
Exactly. Sorry about that, Professor.
That's okay.
Yeah, and then B
On
is
exam, yeah, for everybody on exams, I will be critical. All right.
okay. Yeah. Thank you. And question B is cumulative distribution function of x. So which is FA equals probability of x is smaller than A. So here the upper limit is A and the lower limit is 10, as given x is greater than or equals to greater than 10. Yeah. So wait 1 second.
It's okay. It's okay, because at one point we continue. Right, for integration at one point,
between 8 to
area
10.
0. We can start with 10. Yes.
Yeah. So where we get 1 minus 10 over A from here. So FA, the function is gonna be 1 minus 10 over A. A is greater than 10, and 0 where A is smaller than equals to 10. And part C is we have to find probability.
Hold on, Zakia.
Yeah.
The cumulative probability. Oh, I see your point. Okay. Well, A has to be greater than 10. Do we need to define A greater than 10? Because this is not a density function. But maybe you're right. Maybe you define A, I don't know. But I don't remember we need to define A.
It's a case function, so...
so we need to use Tom?
It's a case function, so we have two cases where A is either greater than 10 or less than 10.
Okay, I think it's
and then,
okay, that's fine.
For cumulative, you have like you get probability of x is less than A for some A. So A can be two cases. It's either greater than 10 or less than or equal to 10.
Oh, I see. Because we don't really know A. All right, that makes sense.
Yeah. And then moving on, part C, what is the probability that of 6 types of devices, at least 3 will function for at least 15 hours? What assumptions are you making? So we are going back to our last chapters. probability of x is greater than equals to 15 for at least 15 hours, which is 1 minus probability of x is smaller than 15. And so we can put, instead of probability of x smaller than 15, we can do 1 minus f of 15. We know fa is 1 minus 10 over a, so we can put 1 minus 10 over 15 here, and the answer is 2 over 3. And now we're gonna use the probability mass function of binomial distribution. We have the probability 2 over 3 we found here, and so the final required probability is we have to find probability of x is greater than equals to 3 for at least 3 function will work, which is equals to probability of x equals 3 plus 4, 5, and 6, up to 6 such types. And here is the formula, probability mass function of binomial distribution. So we're just gonna compute that. And n is 6, x is 3 for probability x equals 3, 4, 5, and 6.
Okay, thank you, Zakia. Let me ask you this.
Sure.
Did you finish the homework yourself or you have some help?
Which homework?
This homework, this one, the presentation. Did you do this all by
No,
yourself?
I did by myself. I did by myself, but still I have some confusion. I don't know. Maybe when I'm gonna keep going, I'm gonna do more exercises. I'm gonna do well. Yeah.
Okay, all right, thank you.
I just follow the examples, like the given examples in the book. Yeah. So.
Okay, all right, that's fine. That's fine.
Yeah. Thank you.
Thank you, Zakia. All right, next one. Oh, Catherine and this Catherine wants to present as well.
Okay, so this is problem 5.14. So we let x be a uniform 0 to 1 random variable, compute E, the expectation E of xn by using proposition 2.1, then check the result by using the definition of expectation. So first we said y equals x of n, x of n. I'm sorry, x to the power of n, and then y equals x to the power, or the lowercase y equals x to the power of n. So first we calculate the cumulative distribution function of fy of y. So and then what we get is y to the power of y over n. And then from there, we calculate the probability density function using the CDF, taking the derivative of that. So we get 1 over n times 1 to the power of 1 over n minus 1. And because it's a uniform random variable, is going to be y is going to be between 0 and 1. So from there, we just do e y, and we calculate the integral from 0 to 1, until finally we arrive at 1 over n plus 1.
Okay. Oops, I don't know why. When I enlarge it so big. Okay, all right, fine. Thank you.
Okay, thank you.
So Darius. Next one.
Good evening, Professor.
Good evening,
Yes.
Xiuyun.
Can you see my screen?
Yes.
So I'm going to present question 5.7. So the density function of x is given by fx equal to a plus b times the
times x to the power 3 when x is greater than equal to 1 and less than equal to 3, and is equal to 0 otherwise. If expected value equal to 5, find a and b. So in this question, we use two functions. One is the probability density function, which is the integral of fx is equal to 1, and the expected value equal to 5. So in here, I first calculate the integral of fx from 1 to 3, which is a plus b times x to the power 3 is equal to ax plus b over 4 times x to the power 4. And just plug in when x equal to 3 minus when x equal to 1. Then we will get the answer is 2a plus 20b is equal to 1. It's the equation 1. And the equation b is the expected value, which is equal to the integral of x times fx. So it's ax plus b x to the power 4, and find the integral, which is equal to a over 2 times x to the power 2 plus b over 5 times x to the power 5, and plug in when x equal to 3 minus when x equal to 1. Then we will get it's 4a plus 242b over 5 is equal to 5. That's the equation b. Then we just find a and b from the two equations. So I use the equation 1 to times 10 and the equation 2 to times 5. Then we will get equation 3 and 4, which have the same 28. So use 4 minus 3. We will get 42b is equal to 15. So b is equal to 5 over 14. And use the b equal to 5 over 14 into the equation a. So it's 2a plus 20 times 5 over 14 is equal to 1. Then we will find the a is equal to negative 43 over 14. Yeah.
Nice.
Mm-hmm.
Okay. Yeah. All right. Thank you, Shoyun.
You're welcome.
Next one. We still have Andreli and Hao and K. Catherine.
I'll go. Oh. No.
I got question number 5.2. A group of construction workers take time X in hours to finish a task. The density function of the time X is below. What is the probability that the workers will take more than 10 hours to complete the task? First, write this to do the integrals of this to find what C is. When you dx it, you get this, and then evaluate from infinity to 0. When x is 0, you get minus negative 12c. When x is infinity, you get 0. And then like I see, it's like 1 over 12. Then it wants you to calculate more than 10 hours. Then you plug in replace the 0 to 10 and plug in C to do it again, and then you get 0.610927 as a result.
Okay. All right. Again, just pure mathematics. We're not able to integrate, then evaluate at the infinity sign. Maybe for probability course. I'll take a look of this book. Because usually when we want to evaluate the probability, we have to use the idea of limit. We use a dummy variable, let the variable run to infinity. But in any case, that's just pure mathematics. All right, so that's how. Next one.
Hi.
Okay, I'm Julie.
I'm doing 5.16, 16. It says the annual rainfall in inches in a certain region is normally distributed with mean of 40 and variance of 4. What is the probability that starting with this year will take more than 10 years before a year occurs having a rainfall of more than 50 inches? What assumptions are you making? So the annual rainfall in inches, population mean is 40 and the variance is 4, and we're trying to find the probability of having a rainfall that is over 50 inches. So probability of x greater than 50, we would convert it to normal variable. 50 and minus the mean, divided it over the variance, which is 50 minus 40 divided by 4. 10 divided by 4 is 2.5. And then on the table, the value that corresponds with 2.5 is 0.0062. That's extra 0, mistake. And then the probability that it will take more than 10 years before rainfall is over 50 inches is 1 minus 0.0062, and then we put it to the power of 10 because it's 10 years, and the answer is it would be 0.9397.
Almost 94%. So it's 2 zeros instead of 3. So the previous one says 1 more 0.
Yeah.
Oh, okay. All right. Okay, you guys are ahead of me.
Yeah.
All right, thank you, Angie.
No problem.
Okay, we have Kay, Catherine, and Aya.
Do you see my screen?
Yes.
Okay, so the question I chose was 4.4, and that 6 men and 4 women are ranked according to the time they took to complete a 5-mile trail run. Assume that no 2 individuals took the same time and that all 10 factorial possible rankings are equally alike. What is the possibility that at least 1 out of the 3 highest ranking individuals is a woman? So we get the probability of the event, which is at least 1 woman, equals 1 minus men times women times complete mile trail run times possible outcomes minus 3, because it's the highest 3 rankings, divided by the total rankings. And from the question, we are given that there's 6 men, 4 women, the 5 is the complete mile run, and 10 factorial is the possible total outcome, and 10 factorial is the total rankings. So we put that into the equation, which we get 1 minus 6 times 4 times 5 times parentheses 10 minus 3 factorial over 10 factorial. And that leaves us with 1 minus 24 times 5 times 7 factorial over 10 factorial, which gives us 1 minus 120 times 7 factorial over 10 times 9 times 8 times 7, because I realized that there's 7 factorials and 10 factorials, which will make it easier for us to remove the top 7 factorial on the top right here, which then comes down to 1 minus 120 over 120, which can be simplified to 12 over 72. So we get 1 minus 12 over 72, which equals 1 minus 0.1666666, which is equivalent to 0.8333.
Catherine, you're behind us. We're at chapter 5. You're still on chapter 4. Anyway, you got credits. Okay, thank you. All right, just one more left, right?
Hi, do you see it? Not yet?
No, no, it's dark.
Okay, give me a second. Oh, okay, I see. What's going on?
Yes.
Okay, it's 511. A point is chosen at random on a line segment of length L. Interpret this statement and find the probability that the ratio of the shorter to the longer segment is less than 1/4, 1/4. Okay, so let x be a continuous random variable with the function f of x 1/L. It's a uniform function. We'll have to consider two cases when, as depicted on the picture above, x to the L minus x is less than 1/4. And the second case is when L minus x to the x is less than 1/4. Okay, in the first case, this ratio is the same as x minus L/5. And in the second case, this ratio is the same as x more than 4/5L. So to calculate the probability, we have to summarize add two probabilities on the first case and second case. So it's probability when x may less than L/5 and plus probability of x more than 4/5L. So the first probability is an integral with a uniform function 1/L from 0 to L/5. And the second probability is integral of a uniform function 1/L from 4/5L to the L. Okay, so and by calculating, that's the calculation, I get 2/5. First integral, from first integral, we get that it's 1/L multiplied by L/5. And from the second integral, we got 1/L multiplied by L minus 1/L multiplied by 4/5L.
Okay. Nice. Thank you, Ayat. Yes, Angeli, to your question. Okay, anyone else like to present? All right. I think some of you are ahead of me. So last class, we talked about continuous random variables, expectations, and variance, how to calculate. So today we're going to talk about a uniform random variable, and some of you already touched the homework on this. Catherine, did you finish grading the midterm? No, not yet. Not yet, sorry. I thought I could. No, I'm not able, I was not able to, not yet. That's okay. That's okay, Catherine. That's okay, I understand. Just do your best, okay? Just do your best. You know, in life, all we could do is do our best. Let's see this one. Uniform random variable. Okay, imagine uniform distribution or uniform probability distribution, just a rectangle, right? The area of a rectangle. Okay, let me read this anyway. A random variable is said to be uniformly distributed over the interval from 0 to 1 if its probability density function is given by this. So when x runs from 0 to 1, it's 1, right? Constant function, horizontal line, 0 otherwise. So this is a density function since the function is greater than or equal to 0, and if we integrate from negative infinity to positive infinity, we will get 1, so it is a probability distribution. So this is just verifying that. Okay, in general, we see that x is a uniform random variable on the interval from alpha to beta if the probability density function of x is given by this, right? Constant, called alpha and beta, representing some real numbers. Constant function, again. So picture it, it's an area of a rectangle. Yeah, just like this, you know, from alpha to beta. And the density function is just this constant function, 1 over beta minus alpha. And what's the area? The area is just this rectangle. Or maybe we have a linear function. If the density function is a linear function or something, right? The picture would be like this. Usually if the density function is a linear function, we would imagine a rectangle. Rectangle? No, a triangle, right? Uniform density function is a rectangle. Linear function give us the area of a triangle. So the cumulative function f of a is for integration from negative infinity up to a, and integrated density function is this. So cumulative function of a, and a of course is in between of alpha and beta. If a is less than or equal to alpha 0, if a is greater than or equal to beta, that equals 1. So in the middle, just a minus alpha divided by beta minus alpha, if a is in between alpha and beta. All right, so that's the cumulative distribution. Okay, just have this a minus alpha over beta minus alpha. Let's see this example. So the random variable is uniform distributed over alpha and beta. So what do we want to find? We want to find expected value of x and the variance of x. So basically we want to find the formula for uniform distribution, expected value and the variance. Well, expected value is defined so, right? For us, it's going from alpha to beta for the limits. And the function f of x is 1 over beta minus alpha, then multiplied by x. So we integrate this, then evaluate at alpha and at beta. So we simplify, so we get, you see, this makes sense, right? Because the area is a rectangle. So this is just the middle, so half of beta plus alpha. In words, the expected value of a random variable that's uniformly distributed over some interval alpha and beta is equal to the middle point of that interval, of course, right? Let's see variance. Variance, we follow the calculation, find the e of x squared. That's f of x, 1 over beta minus alpha multiplied by x squared. Then integrate this, evaluate at alpha and beta, do the calculations, we get this. We get 1/3 of beta squared plus alpha beta plus alpha squared. Now, variance equals to e of x squared minus ex squared. Well, ex is beta plus alpha divided by 2. So that's alpha plus beta squared over 4. Simplify this, we get a beta minus alpha squared divided by 12. So now we have two formulas for, we have expected value, we have variance formula for uniform distribution. So the variance is beta minus alpha squared divided by 12. So the variance of a random variable that's uniformly distributed over some interval is the square of the length of that interval divided by 12. It's the length squared divided by 12. Interesting, huh? Let's see this example. Uniform random variable x over 0 and 10. We want to calculate probability of random variable less than 3, greater than 6, and in between 3 and 8. Less than 3, that means going from 0 to 3 because we started from 0. And the uniform distribution, that's 1 over beta minus alpha, 1 over 10 minus 0, which is 1 over 10. Anti-differentiate, so this is 1 over 10 times 3 minus 0, right? So it's 3 over 10. Okay. For x greater than 6, go from 6 up to 10, 1/10. That's 1/10 times 10 minus 6, which is 4 over 10. In between of 3 and 8, this is 1 over 10 times a minus 3, which is 5 over 10, which is just half. If we draw a picture of a rectangle, right, and we find an area, from 0 to 3, that's 3/10. From 6 to 10, that's 4/10. From 3 to 8, that's half. Right? If we draw a picture. So uniform distribution is easy to deal with. Let's see this example. Buses arrive at a specified stop at a 15 minutes interval starting at 7 a.m. They arrive at, okay, this is similar to one of the questions someone, I think Yongxin presented. 7, 7:15, 7:30, 7:45, so each 15 minutes. If a passenger arrives at a stop at a time that's uniformly distributed between 7 and 7:30, find the probability that he waits less than 5 minutes, more than 10 minutes. So X denote the number of minutes past the 7 that the passenger arrives at the stop. Since X is uniform random variable over the interval from 0 to 30, because we're talking about from 7 to 7:30. So that's why we have this, right? And we use 7 as a mark. It follows that the passenger will have to wait less than 5 minutes if and only if he arrives between 7:10 and 7:15, or 7:25 and 7:30. So the desired probability for this is X in between of 10 and 15 plus X in between of 25 and 30. And then uniform distribution, 1 over beta minus alpha, right? So the 1 over 30 times 15 minus 10, which is 5, right? 5 over 30, 1 over 6. Then this is the same thing. So we have 10 over 30, which is 1/3. Similarly, wait for more than 10 minutes if he arrives between 7 and 7:05 or 7:15 to 7:20. So the probability would be X in between 0 and 5 and X in between 15 and 20. Again, we use 7 as a mark. So do the calculation, that's 1/3. Right, very direct. Okay, let's see this one. This one seems interesting. Oh, this one is troublesome. Let's see this one. Consider random chord of a circle. What is the probability that the length of the chord will be greater than the side of the equilateral triangle inscribed in that circle? Let's see the picture. the chord will be greater than the side of the equilateral triangle. Oh, okay, so basically any equilateral triangle with, let's see. Oh, inscribed in that circle, okay. So imagine I wish to draw a equilateral triangle here, somewhere, right? So the chord, okay, interesting question, let's see. As stated, the problem is incapable of solution because it's not clear what it meant by a random chord. So it could be any random chord. To give meaning to this phrase, we shall reformulate the problem into two distinct ways. The first formulation is this. The position of the chord can be determined by its distance from the center of the circle. This distance can vary between 0 and r, the radius of the circle. Then the length of the chord will be greater than the side of the equilateral triangle inscribed in the circle if the distance from the chord to the center of the circle is less than r over 2. Then by assuming that random chord is a chord whose distance d from the center of the circle is uniformly distributed between 0 and r, we see that the probability that the length of a chord is greater than the side of an inscribed equilateral triangle is probability of d less than r over 2, right? Which is r over 2 divided by r, which is a half. Second, consider an arbitrary chord of the circle. So one end of the chord, draw a tangent. The angle theta between the chord and the tangent, which can vary from 0 to 180 degrees, okay, determines the position of the chord. Furthermore, the length of the chord will be greater than the side of the inscribed equilateral triangle if the angle theta is between 60 and 120. I hope they have pictures to show this. Hence, assuming that the random chord is a chord whose angle is uniformly distributed between 0 and 180, we see the desired formulation is theta in between 60 and 120 is this 1/3. Anyway, let me see how long is a normal random variable. Normal distribution. Okay, this is a long one. Maybe we use 2 classes. So let's start normal distributions. So normal variable, we see x is a normal random variable, or simply x is normally distributed with parameter mu and theta square, and not theta, omega, right? Omega square if the density of x is given by this. Or sigma, thank you. Sigma. Mu and sigma square. If the density of x is given by 1 over square root of 2 pi sigma e to the negative x minus mu square over 2 sigma square. Yeah, I remember when I learned this, I never remember this. I have to reference this all the time. And x can be any real number. So this density function is a bell-shaped curve that's symmetric above mu. Mu stands in the middle. The normal distribution was introduced, de Moivre's bell shape. So we have this mu in the middle, then we'll have 1 deviation apart, 2 deviation apart, 3 deviation apart, mu minus sigma, mu plus sigma, mu minus 2 sigma, mu plus 2 sigma. So in the distribution density function, we see this is 2 sigma squared. So negative x minus mu squared divided by 2 sigma squared. Mu expected value, sigma is the variance. So to prove this is a probability density function, so has to show this equals to 1. Let's see how they show this. So okay, use substitution. Let y equals x minus mu divided by sigma. Then this can change to be e to the negative y squared over 2 dy. But then we need to show this equals to square root of 2 pi. How do we show it? We're going to make I squared. So let's call this one like y, I. Then we'll calculate I squared. I squared basically we have two of this. But when we use dy, we use y as variable. When we use x as variable. Then we have this negative y squared plus x squared over 2 dy. So this is a trick. So we're going to change x squared plus y squared equals to r squared. Then, so this is divided by 2. So we use polar coordinates. We use polar coordinates. Otherwise, you know, how do we integrate this? Because we need, once we change x squared plus y squared equals to r squared, and the dx dy to be r dr theta, we can integrate. Otherwise, we won't be able to integrate. Then we have e to the negative r squared over 2 and r dr d theta. Now we can integrate this. So after integration, we get 2 pi. Then we square root, indeed, I equals square root 2 pi. That's what we want to prove, right? We want to prove this I is called I temporarily equals square root of 22 pi. Because we want to prove this is 1. By the way, this is a classic proof, okay? This is a classic proof for bell-shaped density function. Yeah. So far, I only see this way to prove this, and it's a Q proof. Basically, you use I squared, and then you use the dummy variable, one as x, one as y. Then you use polar coordinates. Let's see this. Important fact about normal random variable is that if x is normally distributed with a parameter mu and sigma square, then y equals ax plus b is normally distributed with a parameter a mu plus b. A mu plus b. Okay. And a square sigma square. Okay, let's see. So let's see y, remember this, y equals to ax plus b. Okay. So cumulative function, right? Then probability y less than or equal to x. Then y is ax plus b. Then we subtract b on both sides. Then we divide by a on both sides. That's cumulative of x minus b divided by 8. Where fx cumulative by differentiation. So now we differentiate the density function of y. So we differentiate this. The density function of y is 1 over a density function x takes x minus b divided by 8. Excuse me. Then, so the density function Oh, okay. So the density, so how is this density function defined? Let's go back. It's defined this way, right? F of x, 1 over square root of 2 pi sigma e to the negative x minus mu squared divided by 2 sigma squared. That's how this density function is defined. So fx, so now the input is x minus b over 8. So we'll have e to the power x minus b over a minus mu squared divided by 2 sigma squared. Then we do some calculations. In the end, we still have e to the negative x minus b minus a mu squared over 2a sigma squared. So this shows y is normal with parameter a mu plus b and a square sigma squared. Basically, this is just changing variables. The important implication of the preceding result, if x is random, x is normally distributed with parameters mu and sigma square, then z, I think this is z score z, equals to random variable, subtract the mean divided by the variance, is normally distributed with parameters 0 and 1, standard normal distribution. Such a random variable is said to be a standard or unit normal random variable. So we want to show parameter mu and sigma square of a normal random variable represent respectively its expected value and the variance. Let's calculate. So we want to calculate e of x, variance of x, when x is a normal random variable with parameters mu and sigma square. So expected value of z, standard, right? Standard and normal distribution. X times the density function with z so f of x e to the negative x squared over 2. Yeah, we can integrate this. Right? Integrate this. Then I see why, right? Why all of you use the negative infinity. Okay, let's just skip the pure mathematics using limits. All right, so we don't need to use the limits. All right. So this book doesn't use it, so we don't need to use it. So we just take the limits for granted. So then evaluate this, so get a negative 1 over square root of 2 pi e to the power negative x squared over 2. Because of the e to the negative, so e term appears in the denominator. When x goes to the negative infinity or infinity, so the e term, 1 over the e term goes to 0. Hence, the variance is ez square, is this guy, minus this, well, this is 0. So just calculate calculation of this. Or we need the integration by parts. So in the end, indeed, we do get 1. So that's so the variance of this standard deviation is 1. It has, right? So expected value equals mu plus sigma times e to the expected value of z. That's still, because e of z is 0. Right? Expected value of the standard normal distribution is 0. If you still remember the standard bell shape. 0 sits in the middle, right? -1 to 1, 1 standard deviation, -2 to 2, 2 standard deviation, -3 to 3, 3 standard deviation. And what is the variance is 1. Sometimes we need to use the chat to find the values, find the probabilities. Let's see this example. So x is a normal random variable, and with mu equals 3, sigma square equals 9, we want to find the probability x in between 2 and 5, probability x greater than 0, probability of absolute value of x minus 3 greater than 6. So the first one, x goes from 2 to 5. Right, we just use this. Greater than 2, less than 5. X, okay, so 2 minus mu divided by sigma, because sigma squared is 9, so sigma is 3. Then this variable x minus 3 over 3. Then the upper one is 5, because x goes from 2 to 5. 5 minus 3 over 3. So which means this z for 3 is in between negative 1/3, 2/3. So this is basically converting into standard normal, okay? Standard normal, something we call z-score, right? Instead of the variable x, we consider with x, the mu can be anything, standard deviation can be anything. But for normal distribution, we can always convert it into a standard one. Standard one means we use z-score. The standard one is mu is 0. So the expected value is 0, sits in the middle. And the variance just 1. So we have 3, 1 standard deviation, 2 standard deviation, 3 standard deviation. Then the outliers, right? So basically, x in between 2 and 5 is the same as the z-score in between of negative 1/3 to 2/3. And we can calculate this, right? Because this is defined for the z. So let's see, from a function getting this, function getting negative 1/3, what's negative 1/3? That's 1 minus this probability of 1/3. I guess this, okay, they use this sign. So it's about 37, 38%. That's for x in between 2 and 5. Right, 2 and 5. That's in between for z-score is in between of negative 1/3 to 2/3. If we look at picture, right? So this is the standard deviation, the bell shape. So think about from negative 1/3 to positive 2/3. So that's the area of this to this. So about 38%. Right. This sign, I guess, just just go to a table to check, right? So 2/3. Let's see. What is a 2/3? 0.6667. 0.66 maybe, or 0.67. So it's about 0.7486. It just didn't write down. Then the negative just indicates 1 minus positive 1/3. So find the positive 1/3, subtract from 1, then subtract from this. So in the end, it's 0.3779. Anyone has any questions? Okay, B is random variable greater than 0. Right. converted into z-score. That's same as z-score greater than -1, right? Z-score greater than -1. The picture is this. Is the area from -1 above. From -1 above. If you remember empirical rule, I think this 34%, 34%. So we think one standard deviation is 68%. The second one, I think, is 13.5, something like that. Then the tail is 2.5. Right? Let's see how much here if we calculate. Excuse me. So greater than -1 is 1 minus this -1 is a 84%, right? So if we use empirical rule, we have 68% plus 13.5, 2.5, 13.5, 2.5, that's about 16. 68, 16, 84%, right? So it's about the same. But anyway, this is this. So this one means to get the value from the table. So for this one, absolute value, z-score calculator. Okay. Now it is still so convenient. So x minus 3 greater than 6. We can also convert this, right? Convert into z-score as z greater than 2 or z less than -2. So do that. That's about 0.0456. Pretty small. Okay, let's talk about this one. The examination is frequently regarded as being good in the sense of determining a valid grade spread for those taking it, if the test scores of those taking the examination can be approximated by a normal density function. In other words, a graph of the frequency of grade scores should have approximately the bell-shaped form of the normal density. The instructor often uses the test scores to estimate the normal parameters mu and sigma squared, and then assigns the letter grade A to those whose test scores is greater than mu plus sigma, B to those whose score is between mu and mu plus sigma, C to those whose score is in between mu minus sigma and mu, D to those whose score is between mu minus 2 sigma and mu minus sigma, and F to those getting scored below mu minus 2 sigma. This strategy is sometimes referred to as grading on the curve. Okay. Since the probability of the random variable greater than mu plus alpha converted into z-score, that's greater than 1, that's 1 minus this, that's about 16%. And x in between mu and mu plus sigma, that's about 34%. Mu minus alpha to mu, same thing, about 34%. You know, bell shape is very symmetric. Bell shape is totally symmetric within the mu in the middle. And the probability p minus 2 sigma and up to mu minus sigma. Convert into z-score. Check the values in the table. So that's about 13.6%. X less than mu minus 2 sigma converted into z-score. Check the value in the table. That's about 2.28%. It follows that approximately 16% of the class will receive a grade A. On the examination, 34% B grade, 34% C grade, and 14% D grade. 2% will fail. Okay, so normal distribution, if we remember we learned before, right, in the elementary statistics class, if a statistics study satisfies certain criterion, then we can use normal distribution to approximate, which makes life so much easier. And here you see this, right? 34%, 34%, that's within one standard deviation. And within two standard deviation on each side is about 13.5%. Within two standard deviation is about, so the tail of it, I think is 2.25%. So that's why you see here, 2.25, about 2%, about 34%, about 34%, about 14%, all right? Let's see this example. An expert witness in a paternity unit suit testifies that the length in days of a human gestation is approximately normally distributed with parameters mu equals 270 and sigma square equals 100. The defendant in the suit is able to prove that he was out of the country during a period that began 290 days before the birth of the child and ended 240 days before the birth. If the defendant was, in fact, the father of the child, what is the probability that the mother could have had the very long or very short gestation indicated by the testimony? Let X denote the length of the gestation and assume that the defendant is the father, then the probability that the birth could occur within the indicated period is greater than 290 days or less than 240 days, or greater than 290 days, this squares this one. And because it's greater than, so we do 1 minus, checking the table, the value 2. Less than, it's just do this. Because this is less than negative, so that's 1 minus this. So about this. Okay, so this means check the value in the table. All right, that's interesting. Okay, anyone has any questions? A lot of examples. Oh, actually 2 more examples. Let's finish. Next one, we talk about normal approximation to the binomial distribution. Okay, let's see this one. Suppose that a binary message, either 0 or 1, must be transmitted by wire from location A to location B. However, the data sent over the wire are subject to a channel noise disturbance. So to reduce the possibility of error, value 2 is sent over the wire when the message is 1, and the value -2 is sent when the message is 0. If x equals plus minus 2 is the value sent at the location A, then R, the value received at location B, is given by R equals x plus n, where n is the channel noise disturbance. When the message is received at location B, the receiver decodes it according to the following rule. If R is greater than or equal to 0.5, then 1 is concluded. If R is less than 0.5, then 0 is concluded. Because the channel noise is often normally distributed, we will determine the error probabilities when n is a standard normal random variable. 2 types of errors can occur. One is that the message 1 can be incorrectly determined to be 0, and the other is that 0 can be incorrectly determined to be 1. The first type of error will occur if the message is 1 and 2 plus n less than 0.5, whereas the second will occur if the message is 0 and -2 plus n greater than or equal to -0.5. Hence, probability of if the message is 1, its error is probability of n less than -1.5. right? That's this one. So subtract 2 from both sides. Okay, that's n less than negative 1.5, which is 1 minus the value 1.5. It's about 0.668%. Then this part is, if the value is 0 and it's an error, which is the probability of n greater than or equal to 2.5. So add 2 on both sides, so n greater than or equal to 2.5, which is 1 minus this, which is about this. All right. Last example. Value at risk, VAR, has become a key concept in financial calculations. The VAR of an investment is defined as the value V, not V, right? Anyway, such that there is only 1% chance that the loss from the investment will be greater than V. If X, the gain from an investment, is a normal random variable, and the mean mu and the variance sigma square, then because the loss is equal to the negative of the gain, the VAR of such an investment is that the value such that 0.01 equals the probability of negative X greater than VAR. Using negative X is normal with mean negative mu and a variance sigma square. We see 0.01 equals to, converting into z-score, then check the value of this. So that's 1 minus this. So this depends on those 3 values. Because as indicated, so 2.33 is 0.099, we see that I see. Because this one minus 0.01 is a 0.99, and what this kind of value equals to 0.99 in the table is 2.33. So that's why this one equals to 2.23, and that means the VAR equals to 2.33 sigma minus mu. Consequently, among a set of investments, all of whose gains are normally distributed, the investment having the smallest VAR is the one having the largest value of mu minus 2.33 sigma. Very interesting. I guess the financial world, the VAR is this. All right, and yeah. Anyone has any questions? By the way, these ones you yeah. Okay, I said by the way of what? What was in my mind? I forgot. Oh yeah, the exam, the midterm. Okay, so so Monday through Thursday I'm pretty busy, but I'll try my best to finish the gradient as soon as possible. All right. Just hold your breath and wait for it. Okay, anyone has any questions? All right, keep up your good work. All right, keep up your good work and keep presenting. And if you don't have questions, you are free bird